Okay, I think we should record in 3 minutes. We haven't yet started. Yeah, vous partagez votre écran.
Thank you, sir.
Yeah, okay.
Lot,
So,
thanks.
est-ce que vous avez envie de parler français? Vous partagez votre écran? Partagez
Oui,
l'audio de l'appareil?
oui, je parle français. J'ai
Ah
vécu en
oui,
France.
bien
Oui,
sûr, on peut parler. Ah,
oui.
ah,
Mais
C'était une fois que un mathématicien russe nous avons nous avait demandé est-ce que по-русски Кашаев спросил, можно у вас тут сделать какой-нибудь портаж? Портаж it's screen sharing, but he asked
oui,
for a French word. Yeah.
yes.
Можно у вас тут какой-нибудь портаже сделать? Да, портаже это да, ну
Mm.
как это вот сейчас у нас по-русски говорят, сейчас часто люди говорят расшарить экран, какое-то совершенно такое странное слово, но он спросил, нельзя ли здесь сделать портаж. Est-ce que vous
Actually,
pouvez
I
partager
don't.
votre écran? Yeah, de temps
Yeah,
en temps, on peut utiliser le mot share, but yeah, ok,
yes.
c'est bien, c'est bien. Ah,
Je parle russe aussi un peu.
est-ce que vous parlez russe?
Un tout petit peu. J'ai appris à l'école.
Ah,
Я
ah,
говорю чуть-чуть по-русски.
очень хорошо. Très bien.
Да.
Очень хорошо. Donc, ah, so we will start in a minute.
Yep.
I think so. You may cut our discussion for the first 3 minutes, uh, and so it's already being recorded, I think. Yes, and so in a minute we will start. Mm.
Okay, so
Just a moment, just a moment. Dear friends, let's start our today's talk. Our speaker is Raphael Pinarbasi, and he will tell us about new generalizations of Sedrakyan's inequality, Tito's lemma. And let's welcome.
Thank you, sir. Hello, my name is Raphael Pinarbasi, and yes, I will present generalizations of Sedrakyan's inequality, otherwise called Titu's lemma, and the equality conditions. So last time we presented this, actually, Haik Sedrakyan presented it in the same seminar, but we added more applications and more applications related to knot theory, distance geometry, some more interesting applications. So I'll go over the paper again, and then at the end we will see the applications. So let's look at the abstract. In this paper, we established several generalizations of Sedrakyan's inequality, otherwise called Titu's lemma, referring to the article about the applications of one useful inequality of Nairi Sedrakyan, published in 1997, and to the book Mathematical Olympiad Treasures of Titus Andreescu, published in 2003.
Okay.
If you
Excuse
guys
me.
have, yep.
How are Nairi and Haik related?
How Nairi and Haik relate?
How are they related? Are they relatives?
I believe Nairi Sedrakyan is Haik Sedrakyan's father.
Okay. Okay.
I believe. I'm not sure, but I think so. Yeah. If you guys have any questions during the presentation, you can ask for sure. So, here's the introduction. So here we can see at the bottom that there's the initial inequality of Sedrakyan's inequality or Titus lemma. And here I'll read it for you. So let A2, etc. until AN be real numbers, and B1, B2 until Bn be greater than 0. Then we have this inequality where a1 squared over b1 plus a2 squared over b2, etc., until an squared over bn is greater than equal than a1 plus a2, etc., until an is squared over b1 plus b2 plus b3, etc., until bn. So I'll let you take a look at it. Okay, so the first thing that we did is we generalized it for cubes here, as we can see. So it is the same thing here, and here we can see that it is with cubes, and there is more than one term here. We can see. I'll let you take a look at this, and then we'll go to the generalization with kth power. Okay, so here we have the generalization for the kth power. This is the most important one. As you can see, there are k minus 1 terms here, and here we can put any power to the power k. So this is our main result, and we'll go over the proof and the equality conditions right after. So here I'll let you take a look at this. Okay. Let's go into the equality conditions. Let's look at Sedrakyan's inequality first. Here, the equality condition is a1 over b1 is equal to a2 over b2 is equal to a3 over b3, etc., until an over bn. Then, for the generalization for cubes, we have a similar thing, and here it's a1 over b1 equal to a2 over b2, etc., until an minus 1 over bn minus 1. And then we have this also, b1 over c1 is equal to b2 over c2, etc., until bn minus 1 over cn minus 1. And here for the kth power, it's you can see there's more columns, so it's the same thing. A1 over b1 is equal to a2 over b2 until n. Here the same. Here we have many amount of like we have k times the columns. So it's b1 c1 here, and then here will be c1 d1, c2 d2, etc. until n. And then here it goes until y1 over gamma 1 is equal to y2 over gamma 2 is equal to y3 over gamma 3, etc. until is equal to yn over gamma n. I'll let you take a look at it, and then we'll go to the main proofs. Okay, let's move on. So proofs of the inequality, so the initial one. This is the section where we provide the proof of Sedrakyan's inequality, otherwise called Titu's lemma. In the next section, main results and proof, we provide the proofs of the generalizations and their corresponding equality conditions. So, at first, we want to prove the following: this Sedrakyan's inequality or Titu's lemma. So, in order to prove this inequality, let us start with the case of two terms, that is, let a be greater than 0 and b be greater than 0. Let us prove that this inequality is true. So, we rewrite this expression using a common denominator. As we can see here, we multiply by b and then by a. We have a common denominator. Then we cross multiply to get this expression. I'll let you take a look at it. Then we cancel the common terms. As you can see here, we canceled y squared ab here and y squared ab here. We canceled x squared ab here and then x squared ba here. So we get this. And then we rewrite it this way. So we bring 2xyab to the left side here. And now we can complete the square to get this. And as the square of any number is non-negative, this ends the proof of the initial statement, as you can see here. So, using the case of two terms, we will prove that the statement with three terms is true. So now we can see that there's three terms. It's x squared over a plus y squared over b plus z squared over c is greater than or equal than x plus y plus z squared over a plus b plus c. So here, denote x plus y as a capital A, and a plus b as capital B. Then using the statement for two terms, we get this. So this is equal to this, which is greater than or equal than this, because we used the formula with the two terms that we just proved, which is equal to this. So it follows that this expression is greater or equal than this expression, which is greater or equal than this expression, which is equal to this. This ends the proof of the statement for three terms, as we can see that this expression is greater or equal than this expression. If you guys have any questions, you can ask. In a similar way, we can prove the case for four terms and have the same results with more terms like 5, 6, 7, up to n terms, where n is any positive integer, because we will do the same process again. We will denote them as a capital letter and then combine them to have the same inequality with two terms, and then that will be the proof. So now let's go with the equality conditions for two terms to the second power. Let us prove the equality is possible for two terms. So here we have the equality condition, like we put the equal sign and then we rewrite with the common denominator on the left side again. We cross multiply as we did for the proof, and then we cancel common terms and we complete the square as we did again. And this is true when ya is equal to xb here. So it follows that the equality condition is x over y is equal to a over b. If this is unclear, please ask. I'll let you take a look at it, and then we'll go to the equality condition for three terms. Okay. So the equality condition for three terms to the second power. Let us prove the equality is possible for three terms. So x squared over a plus y squared over b plus z squared over c is equal to this. So for the equality condition, we have x over a is equal to y over b. In a similar way, we have that x plus y over a plus b is equal to z over c, as we did last time. So denote x over y is equal to y over b is equal to k. Then x is equal to ka and y is equal to kb. Then you plug this in to get ka plus kb over a plus b is equal to z over c, and we obtain this as we factor k out. Then we can cross a plus b here, a plus b here, and we can say that k is equal to z over c. So now it follows that the equality condition is x over a is equal to y over b is equal to z over c. So I'll let you take a look at it and then we'll go on. Okay. So the equality condition for n terms to the second power. So in a similar way, we can get the inequality condition for 4, 5, 6, 7 until n terms, where n is any positive integer. So it follows that the equality condition for n terms is this. So a1 over b1 is equal to a2 over b2 is equal to a3 over b3, and then we go on like this until it's equal to an over bn. I'll let you take a look at it, and then we'll go on.
Any questions?
No questions?
No, so far not.
Okay, I'll move on then. So now we can move on to the main results and proofs. So we can start by the generalization for cubes. So let B1, B2, C1, C2 be any positive numbers. Then we have this. Now for the proof, we rewrite it using the common denominator and opening the parenthesis. So you can see that here we open these parentheses under the fraction, and above the fraction with the cube, we opened it. And here we rewrote it with a common denominator, and we got this. Then we cross multiply to get this long thing, and we will cancel the common terms on the left side and the right side, and we will get this inequality. Then we will apply the inequality a plus b plus c is greater than equal than 3 cube root abc to get these two inequalities. So as you can see, to get these two ones, we took 1, 2, and 3 from this side, and then 1 from this side. And then we took 3 expressions here again, and then 1 expression from here to get this. So we took these 3, which is greater than equal than this, because we used the inequality here, which is equal to this, which is already here, as you can see. And we did the same here. So this plus this expression is greater than equal than 3 cube root of this, which is also equal to this, which is this expression. So now, summing up the last two inequalities ends the proof, as we can say that this is true because of the inequality, and then this is true because of the inequality that we applied, which is equal to this and this, which we already have here. So if you guys have no questions, I will move on to the equality condition. So it is known that in the inequality a plus b plus c is greater than equal than 3 cube root abc, the equality holds true when a is equal to b is equal to c. As we saw there, this means that this is the equality condition and this. Now, let us prove that the equality condition for cubes of 3 terms is a1 over a2 is equal to b1 over b2 is equal to c1 over c2. So we say it again here, it is known that in this inequality, the equality holds true when a is equal to b is equal to c. So we equalize these, and we cancel like terms to get this expression, and we divide by b2 and c2 to get this, which is b1 over b2 is equal to c1 over c2. And now let us equalize these two terms again to get these and these two also, like we did for the first one. Then divide one equation by the other to obtain this equality. and then we cancel similar terms to get this. C1 over C2 is equal to A1 cubed C2 squared over A2 cubed C1 squared. And since B1 over B2 is equal to C1 over C2, we can rewrite C1 over C2 as B1 over B2. Then we divide by B2 squared over B1 squared, and we get this, which is, as you can see here, it's B1 cubed, and here it's A1 cubed, and here it's B2 cubed, and A2 cubed. So with that, we can affirm that
Excuse
B1,
me, a crazy
yeah,
question.
yes,
Does it have anything to do with chain fractions?
chain fractions. That's a good question. The thing is, I'm not really informed in that field, so uh,
I'm now interested in
yeah,
triple chain fractions when we want to deal with three numbers instead of two numbers. And
okay.
actually, for a pair of numbers, we have such a lot of nice results. And maybe so you are doing some induction of passing from two to three and from three to four. And
Yeah.
maybe if there is any connection, it would be great to know.
Oh, um, uh, um, I'm not really sure actually. Maybe in the applications we wrote it since I did this paper with Sedrakyan, but I don't think I will be able to answer that by myself. Honestly, I'm not really informed in that, but yeah, we do use induction hypothesis there. Uh, I just don't know how to apply it to your topic specifically. So it's fine for you if we see it in the applications, if there's anything there, maybe. Hello? Is there a technical problem?
Yes, sir.
Oh, yeah, is there a technical problem? Uh the guy that asked the question is not answering anymore.
Okay.
Okay, should I wait or wait? Let's see if we
No,
can.
please go on.
Oh, okay, okay. Yeah. Okay. So now we have the equality condition for cubes, and we can move on to this. We're gonna prove it with three terms now. So here is the inequality with cubes and three terms. As we can see, one, two, and three terms. Now the proof, using the inequality for cubes with two terms, we get this. So now let us prove that this inequality holds true. So denote A1 plus A2 as X, then B1 plus B2 as Y, and C1 plus C2 as Z. Then applying the inequality for cubes with two terms, we get this inequality. So,
As far as
uh,
I see, you always have the same, more or less the same induction argument for the
uh-huh,
any number
yes.
of terms and for any inequality. Yes, and so do you have anything maybe striking to add to the proof, or
Uh,
maybe you are soon going to pass to applications?
uh, no, it's just like to show the process
Yeah, sure. Yeah, please
of
go
the
on.
proof. If you want, I can do it a bit faster. I can go a bit faster with the
No, no, no,
proof.
no, no need to go so that faster, but I think
Uh-huh.
I have grasped the main idea.
Yeah, it's to show how we got to the proof and how we used we see the same logic in the same like with the cubes of three terms, and then we're gonna say that it's the same for the cubes of four, five, and up to n terms. So here we denote the same thing. A plus A1 plus A2 is equal to X, b1 plus b2 is equal to y. Then here we get this expression. And then we use the inequality for cubes of two terms, as we proved it already, and we get this. And this ends the proof, as we proved that this inequality holds true. Then the equality condition for cubes with two terms is a1 over a2 is equal to b1 over b2 is equal to c1 over c2. So in a similar way, we need to have the following equality condition: a1 plus a2 over a3 is equal to b1 plus b2 over b3 is equal to c1 plus c2 over c3. So we denote this as k equal to k. Then we get a1 is equal to ka2, and b1 is equal to bk2, kb2, then c1 is equal to kc2. We plug it in to get this expression. I'll let you take a look at it. Let's move on. Then we get this as we factor k plus 1 out. You can see. And then we divide by k plus 1 here, here, and here. And we get a2 over a3 is equal to b2 over b3 is equal to c2 over c3. So the equality condition for cubes of three terms is a1 over b1 is equal to a2 over b2 is equal to a3 over b3. And then here we have the same thing with b and c.
In any case, you use that the fact that the arithmetic mean is greater than the geometric mean.
Oh, I don't think I understand your question very well.
Well, I
actually.
mean, when you write that a plus b plus c over 3 is greater than cube root of a b c, it's arithmetic mean and geometric mean.
Oh, that formula?
Yeah.
Okay, yeah. Yeah, we use that. Yeah. So I'll move on.
Yeah, sure.
And we proved the inequality for cubes of two terms then, and the inequality for cubes of three terms, as we saw here. And in a similar way, we can get the inequality for 4, 5, 6, 7, up until n terms. So we kind of did it in the same way. And so here, and the equality condition for cubes of n terms is this. I'll let you take a look at it. This is the cubes, and this is the equality condition for cubes. So as you can see, we did the same thing. So we proved it for two terms, three terms, then we jumped to n terms. And yeah. Now let us try to generalize this inequality for higher powers, or actually any power. And we start with two terms. And let us prove the following generalization, which is this one. So we proceed to prove by mathematical induction with respect to k, and this is the base case. If k is equal to 2, then we need to prove that this inequality holds true, which we already did. It's 4 squared. We already proved this. Now, induction hypothesis here. Assume that the statement is true for k is equal to m, then let us prove that the statement is true for k is equal m plus 1. So we have this, and we need to prove that the following is true of m plus 1. And in order to be able to use the induction hypothesis for k is equal to m, let us rewrite this inequality in this way. So as you can see, the m plus 1 came down here, and as we divided by a1, and we connected b1 and y1 here. so we have it visually in one place. Then let us rewrite let us use the induction hypothesis, since we now have a1 to the power m, assuming that the first inequality of the induction hypothesis is true. We get this inequality, where the equality condition holds true when a1 over a2 is equal to b1 over b2 is equal to c1 over c2, etc., until gamma 1 over gamma 2 is equal to y1 over y2. Then, using induction hypothesis, we get that this. I'll let you take a look at it. Then, to finish the proof for n plus 1 power, we need to prove that this inequality holds true. Then we cancel like terms. As you can see here, all of the inside things, we cancel them. And then we cross multiply, and we get this expression. Then we cancel like terms. As you can see, we cancel this and that. And then we get this expression. Then we rewrite this expression like this. As you can see, we took the common denominator and we multiply with a1, a2 on both sides to get this expression, and we rewrite it like this. So we rewrite it like this so that we can factorize, and then we get this expression, and we rewrite this expression like this. So we can say that b1 a2 minus b2 a1 is greater or equal than 0, as you can see here. And it follows that b1 a2 is greater than equal than b2 a1, and also that b1 over b2 is greater or equal than a1 over a2. And we do the same with this side, with y2 a1 minus y1 a2. Here it's greater than 0, so y2 a1 is greater or equal than y1 a2. We do the same thing again, and we get this. So now we can affirm that b1 over b2 is greater or equal than a1 over a2, which is greater or equal than y1 over y2. And now, by homogeneity, we said that a1 over a2 is greater than equal than b1 over b2, which is greater than equal than y1 over y2. And since these two contradict each other, we can say that only the equality condition holds true here. So this is the equality condition, as you can see. So here we have this for two terms, and here you have the equality condition. I'll let you take a look at it, then we'll move on. So
Sure.
now we do with three terms. The same thing again. We have 1, 2, 3 terms and minus 1. And here we have this. So we have this expression. We rewrite a2 plus a3 as a prime 2. And then we do the same with b, c, gamma. And here we have this new inequality now, and we already proved it. Then the equality condition is the following: a1 over a prime 2 is equal to b1 over b prime 2. So here's the more tricky part. So here we have this. Then we denote a1 over a2 is equal to b1 over b2, etc., until equal to k. Then we plug it in to get this and this. So it follows that the equality condition is this: a3 over a2 is equal to b2 over b2 is equal to c3 over c2, etc., until gamma 3 and 2, and the full equality condition is this one. So A1 over B1 is equal to A2 over B2 3 times because we have 3 terms, and then the same thing here, 3 terms, and we have as many column as we have of powers, and then here we have y1 over gamma 1 is equal to y2 over gamma 2 is equal to y3 over gamma 3, and in the same way as 2 terms, 3 terms, we can prove this for n terms. So this is the thing that we got at the end. This is the inequality that we got at the end. And the equality condition for this case is this one. As you can see here, we have more terms here. We have n terms. And here also we have as many as the power here. I'll let you take a look at it. This is important.
Okay.
So now we can go to the applications to illustrate the usefulness. I think this would be more interesting. So these inequalities, both squares and their generalizations for cubes and the nth power, can be applied in various areas of mathematics, such as algebra, algebraic inequalities, geometry, distance geometry, knot theory, and more. We provide below a few more examples. So here we can see the first one is the mathematical Olympiads and problem solving. We have number theory, discrete mathematics, we have mathematical analysis, we have
So what will be
optimization.
mentioned explicitly? So which of them are you going to give all those examples
Yes.
explicitly?
Yes,
Oh,
yes.
great.
Yeah, I have all of them here, and we'll go over all of them. So how we applied it.
Okay.
So here we have some other examples here, you know. Yeah, so we can start with the first one, application 1, national math competition, grade 11 to 12 in Armenia, 2026. So this was really interesting because as we finished the paper, we were trying to see if the results that we got were actually useful, and it turns out that a couple days later, there was this national math competition in Armenia, and for this problem, they took a long time to solve it, but with our inequality, it took way less time to solve it. So it was very effective. So let's see. This is the example. So let n be a positive integer and a, b, c be real numbers such that a, b, c is equal to 1. Prove that this inequality is true. So the proof of the application. So let us rewrite the inequality like this and apply both Sedrakyan's inequality for squares and the generalization for nth power. So here, if you guys have any questions, it might be a bit confusing, you can ask, but we'll go over it down there. So here, look at this. And then here's how we did it. So here we applied the inequality for squares. As you can see, 1 over 1 plus b plus 1 over 1 plus c, etc. Is greater than or equal than 1 plus 1 plus 1 squared over 3 plus a plus b plus c.
And can I see the second term? Excuse me. So you had
Yep.
a plus b plus c to the n over. So in the previous page.
In the previous page,
In the
yeah, here.
previous page, you had.
So it's this one, then this one,
Yes.
then this one. You see, we took them.
So where does 1 plus 1 plus 1 to the n minus 2 come from? Yes, so I mean the last term.
Yeah.
The last term.
This one?
Yes. So the last term.
Yeah, this one. Okay, I'll tell you. Just give me one sec. So here you can see that 3 plus a plus b plus c goes here, right? And then plus this part, we have it here because we did it in 2 parts. You see, we took this
So the
expression.
first part is clear, but the second.
Yeah, so we'll move on to the second. And now here we use the generalization for nth power here, and it's a to the power n over 1 plus b, etc. here like this. And then here we have this. Then we got this under.
So I don't understand n minus 2. Where do you get n minus 2?
Actually, it was confusing for me also, but then I understood. I need to take a second to think about it. The thing is, we didn't write all the steps here to make it less long,
Ah,
but
okay, okay.
then
Now
it
I see. Yeah.
confuses. Yeah, but then it gets confusing. So I'll try to understand it. One second. So here we have this. So, n minus 2. Minus 2 times. Oh, I can't really remember it without the steps. I'm really sorry, but we did it with Hike actually, and I understood it. And yesterday I asked him the same question, like how did we get this, and then I understood it, but I don't know why right now I can't seem to figure it out. But yeah, we don't have the steps, so yeah, I'm really sorry. I'll try to make it clearer, and then I'll get back to you. So let's continue if that's fine with you. So in order to be able to apply the inequality of nth power, we take b1 is equal to 1 plus b, and the same thing here, b2 is equal to 1 plus c, b3 is equal to 1 plus a, and c1 is equal to 1, c2 is equal to 1, c3 is equal to 1, and gamma 1, etc. So we get this expression after applying all that, and we plug in the values of b1 is equal to 1 plus b, etc., and we get this expression. I'll let you take a look at it.
Okay.
And in order to finish the proof, we need to prove that this plus this is greater than or equal than 3. So now we're trying to prove this. So then with the common denominator, we can addition to get this expression. And we rewrite it as this, as you can see here.
Well, but it's not as short as you were telling. So you use two formulas, but
Yeah.
but after that, it's not
Yeah.
obvious.
Okay, I agree. It's not that short. But I'm pretty sure when I was talking about it with Hike, he was telling me that they took like the 30 minutes or like 1 hour to solve it, like the very, very long problem. It's maybe not magical. The generalization is not magical, but I think it helped very much here in this problem. So here we cross multiply to get this, and we denote a plus b plus c as x, and then the last inequality is equivalent to proving that this inequality is true, and we need to prove that x to the power minus 1
Yes, please
Yep.
show the previous page once more. Please show there is a question on the chat. Yes.
This.
Yes.
Yes, so this is the main question. Should I move on? Yep. Okay. I'll move on. So here we got to here. So we need to prove that x to the power n minus 1 is greater or equal than 3 to the power n minus 1. And that is x is greater than equal than 3. And equivalently, we need to prove that a plus b plus c is greater than equal than 3. And given that abc is equal to 1, from AMGM, we get that a cubed plus b cubed plus c cubed is greater than equal than 3abc. And so, therefore, a plus b plus c is greater than equal than 3 cube root abc. And 3 cube root abc is the same as 3 because ABC is equal to 1. So 3 is equal to 3. So this is the end of the application. So next we have application 2. So let ABC be a triangle with sides A, B, and C. We can see the figure here, ABC. Then we have HA and HB and HC be the corresponding altitudes, and we need to prove that this inequality is true. So R is the in radius, and we need to prove this. So according to Sedrakyan's inequality or Titu's lemma, we have this inequality. We have this inequality. So to prove the initial inequality, it is enough to prove that this inequality is true, as you can see. So canceling a plus b plus c on both sides, we get this. So we cancel a plus b plus c. Then we divide both sides by 2 to get this expression, and we did it because of this, because S is the area of the triangle, and let us use the following well-known formula, which is this one. So it follows that this is smaller or equal than S, which is the area. And now this is 3s over 3, so we need to prove 3s over 3 is smaller or equal than s, which is already the 3s over 3 is already s, so the s is smaller than equal than s, so this already ends the proof. Okay. Now in application 3, we have knot theory. So this inequality can be used in knot theory as well. The rope length of a knot is the minimum length required to tie it. So this is the example. Estimate structure by applying Sedrakyan's inequality or Titu's lemma. We get the following. So we get this thing. So this is just the application. I'm not really deep into the subject, so I don't know how we use it, but I'm sure that it would be
Yes,
useful to. Yep.
excuse me, you mean a rope length when our knot has width 1 or what? Rope length. Of our knot. Well, it should have width 1, right?
Yeah. Then with 1, yeah.
Yes, and also it looks like
Yep.
all those equalities should have continuous analogs because when you take a sum and you can go to the limit, you should have an integral. And rope length is well not discrete usually,
Okay.
but
Okay, yeah, so there's more to go into this into into this, right? Yeah, maybe we didn't go as deep. We just took the Sedrakyan's inequality and we only used it, but yes, I agree for sure there will be more to go into, like, and go deeper into the subject. And here we can see Ki is the curvature contributions and Li is the arc length. And here we use the Sedrakyan's inequality or Titu lemma. So for sure we can go deeper into these applications, I think. And here, so does anybody have any questions?
There is a question on the chat. Can I change the edge's name for the triangle? I don't quite understand what it is, what it is meant.
This?
It's about the previous picture, excuse me.
This one? Application 2?
I think so. I think it was already.
Yes, absolutely.
Yeah, application 2. Okay. So here it's let's go back to the application 2 to see. So here it's number theory, or yeah. So here in application 2, we have this problem, and as you can see with the steps, we solved it with Sedrakyan's inequality here. What is the specific question?
Question is the edge's name ABC. Can I change CD?
Sorry, can you repeat, please?
Replaced
I didn't.
replaced by CD. I think so.
Please. ABC.
DEF. Can I change for this format?
Oh, I'm sorry, I didn't understand.
Please show statement of this position.
This
This application number 2.
application number
Uh,
2, yeah.
let ABC.
Yeah, let ABC be a triangle with sides
I
ABC.
asked. I asked the questions. Let DEF.
DEF, okay.
So
Oh,
can
okay.
you do this?
If we change it with DEF,
Yes.
um, yes, if it's
May or may
so
not be.
yeah, so if it's DEF instead of ABC, and then
Can
we
I
have
replace this? Can I replace this ABC in the DEF?
yes, you can replace it will be the same exact it will be the same exact process with the different letters.
Okay. Okay. Thank you. Thank
Yeah,
you.
yeah. So this figure we did it actually. So yes, it wasn't given exactly like this. We constructed it and we plugged it in. So yes, it's not. It could be a bit different, you know. It's not exactly with the same proportions or anything. It can be a different letter here, here, here. So yeah,
Okay. Okay.
I
Thank you.
hope that answered your question. So application 3, if nobody has any questions, we'll move on to application 4. So
Yes,
here
please.
we have application 4, bounds of sums of squared distances. In distance geometry, you often analyze expressions like this, where di is equal to distances and y1 is equal to positive weights, edge lengths, uncertainties, or masses. And here this is what they analyze. This is the expression, and we used Sedrakyan's inequality or Titus lemma to get this expression. So uh, me with Sedrakyan hike, we figured out that this gives the lower bounds for total distance-based energies, and we thought that this would be interesting for some of the people in the seminar. So here you can see how we used Sedrakyan's inequality.
Okay.
Okay. So application 5, sensor network localization. In many problems of distance-based positioning, we know distances from sensors to anchors, typically least squares objectives. It's this, and we apply Sedrakyan's inequality on this, and we get the following. We get this inequality, as you can see here, and this will help for error propagation, stability of reconstruction, robustness of localization algorithms. If there's no questions, I'm going to move on. So application 6. So stress functions in multidimensional scaling. In multidimensional scaling, MDS, we reconstruct coordinates from pairwise distances. The objective often looks like this. And again, here we are going to apply Sedrakyan's inequality or Titu's lemma. We get the following expression, where dig is equal to model distances and delta ig is equal to observed distance. Here. So I'll start with application 7. If anybody has any questions, just cut me and ask me, okay? Application 7, where the generalized nth power could appear. So the power version, here we have this expression. And now we can finally apply the inequality for nth power, and we get this. And it could theoretically appear when bounding distance energies, graph embeddings, network stress functions, and these show up in distance geometry optimization, spectral graph theory, geometry analysis. So I think this would be useful. Here. Move on to application 8. So polygonal knot energy estimates. So in geometric knot theory, a metric side of knot theory.
Well,
Yes.
as a knot theorist, I want to have estimates in terms of something. So, for
Okay.
example, in terms of the number of crossings or in terms of the number of, so I don't see any estimates. So
Oh.
assume I have a trefoil. How can I have this estimate?
Okay. So yes, it might be not as we might not have went as deep in the subject. So yeah, I agree. We should for sure go deeper and show more usefulness in the generalization. But yeah, for now, I apologize for not having
Well,
this.
excuse me.
Yeah.
So can you organize a separate meeting with Hike and with me,
Yeah.
and maybe with some of my students, so that we could be able to discuss applications to knot theory, especially. It would be
Uh-huh.
important for us.
Okay. Yeah, if it's interesting for you guys, it's interesting to me
Sure.
also. I will learn more about knot theory because I'm really not in depth in that subject. So I'll note it down right now, and I'll ask Ike Sedrakyan to do a meeting all together.
Sure. Okay.
1 second, I'm sorry. I'm just noting it down so I remember. Knot theory. Okay, let's move on. So, application 8, polygonal knot energy estimates. So, in geometric knot theory, a metric side of knot theory. So, knots are often approximated by polygons with edges EI. So, many knot energies depend on pairwise distances between segments, and E is equal to this expression, as we can see. By applying the inequality for nth power, we get this, as you can see here. So this is the result of the applying the generalization. So let's move on. Application 9. Discrete distance energy bounds, distance geometry. In distance geometry, one studies configurations of points P1 to Pm with pairwise distances dig. Many optimization problems involve distance energies, for example, this, where yig is greater than 0 or weight. And here again, we can apply the nth power Sedrakyan form, and we get this inequality. So this gives a global lower bound on total distance energy based only on the sums of distances and weight. So such bounds appear when studying rigidity problems, embedding distortion, weighted distance matrices. Here we can see the result that we got from using the generalization. I'll move on to application 10. Here, bounding.
Well,
Yes.
you are talking about graph embeddings. So can you have any consequences? So for graphs embeddings, we have some genus of embedding, or we can have some, if we have an immersion, so we have some crossing numbers of embeddings. So there are concrete values for embedding for graphs in graph embedding theory. So can we estimate them?
Can we estimate them using the generalization? So
Yes. So usually, no theorists speak one language,
okay,
diagrams, crossings, and graph theorists speak another language.
okay,
These estimates should somehow fit into those languages, I think.
okay. Yeah, probably, I just not advanced enough in the subject to make any claims. I think I should answer that with Hakserakan when we do a meeting together with your students. I'm sure he will know how to answer those questions better, as I'm not well into that subject, let's say. So yeah, but probably yeah. So here I'll present this in geometric embeddings problem topic connected to distance geometry. One minimizes a stress functional, and here this is the expression where dig is equal to realized distances, and well, delta ig is equal to target distances. And using the generalized Sedrakyan's inequality, we get this inequality. And this gives a lower bound on total embedding error. These ideas appear in multidimensional scaling, network embeddings, and rigidity optimization. And yeah, this is how we used it. And I think this is about it. Yeah, here we have the references if you guys want to take a look at it. And yeah, this was the last application. Is there any questions?
Okay, any more applications?
We don't have any more applications for now.
Well,
These were the 10 applications here.
it has already been great. So
Yeah.
I really enjoyed the talk. Actually, I
Mhm.
think you can give talks for our mathematical circle. I think Hike already gave it. So about some Olympiad problems, it would be very nice. So people are asking about the PDF file. Please send it to us. So are
Okay.
there any questions or comments concerning this paper, this talk? Maybe any comments? Well, if it's not the case, so let's thank the speaker again. It was a very nice talk, and let's
Thank
meet
you
with
so
you
much.
Please
separately.
show references again.
Yeah, here.
Thank.
Oh, it was published in Quant. It's interesting. Yeah, great.
Yeah, thank you so much, everyone. Also, I really appreciated giving this talk.
Thank you.